Good afternoon, ladies and gentlemen. Thank you all for being here. This paper was supervised by Professor Chang. We're students of National Tainan Girls Senior High School. Since Professor Chang is on flight, we'll represent him to give a lecture on development of innovative micro-SMA-wire drive robot in engineering education. I'm going to present the abstract, introduction, and fundamental measurement. First of all, I would like to describe the abstract. First, our goal is to make an innovative rotary actuator by utilizing linear SMA integrated with friction drive and ratchet. Second, functional independent principle is employed to facilitate system development. An innovative robotic system which consists of master-slave rotating subsystems. Our background is, first, this project was proposed by two high school students. Second, the micro-SMA-wire drive Lego robot has been implemented by non-engineering students through a one-year hands-on self-learning process. Introduction. This paper has two aspects. One aspect is research and development. Shared memory alloys can produce phase transformations in accordance with temperature changes, which can be used in actuators of robots. In this project, we made linear and rotary SMA actuators to drive robotic arm and gripper. Another aspect is education. In this project, students are not required to be familiar with any mechatronic system, not even any engineering field. Students need to build their own knowledge with 3 hours a week lab course in one-year project. This learning and research subject was initiated by students with proposals submitted on May 13, 2020. Students learned basic engineering knowledge under the detailed guidance of advisor in the first 3 months. Finally, the project was completed in NCAR Optometronic Systems Control Lab. Project of developing educational robot. There are 4 objectives of the project. First, explore the characteristics of SMA wire. Second, design and manufacture of micro-wire SMA actuators. Third, apply SMA actuator to a robotic system. 4. Use Arduino and write programs to control SMA robot. About the conceptual design and constraints. Our innovative design. To decompose two-dove rotational motion of spiral, so that pick-and-place operation can be realized by coordinating 2 independent rotational subsystems. Manipulator system, which consists of robotic arm and gripper, and feeding system, as shown on the slide. Material constraints. Available vaccinal SMA wire, structural material by Lego blocks, and other materials. Fundamental measurement. A. Measurement systems. The measurement system is established by students for various experiments. Only fundamental tools and devices including school, balls, ruler, center weight, breadboard, thermometer, mobile phone, digital multimeter, and checker software are available. B. Characterizations of SMA. First, movement, stroke, and response speed. We installed the SMA with barrel spring in 2 different ways as shown on this page. The linear type and the V-type. It is found that the movement of the V-type will produce a larger stroke. In addition, the cooling time is about 3 times of heating times in the cycle of stroke. Second, Young's modulus. For the relationship between the stress and the strain, the calculated modulus is 2009 GPa, which is a result in the martensite phase at room temperature 24.05 Celsius. Third, resistance vs temperature under different loads. We saw SMA testing setup as shown in this figure. The heating hot pipe is used as a constant temperature reservoir, and the loaded SMA is connected to a multimeter to measure the resistance change under different loads and temperatures. Experimental data shown in figure reveal the hysteresis phenomenon. The hysteresis behavior will cause the SMA to heat and cool with different deformations. 4. Thermistor calibration and measurement. The 76 μN SMA is a very thin wire, and only small amount of heat is generated to cause temperature rise in the sensor. We innovatively decided to use a thermistor, which is wrapped by the SMA wire for sensing the temperature of the SMA in the circuit, as shown in this lab figure. At first, we measure and calculate the thermistor parameter. Then we can calculate the temperature of the SMA. After heating to be 113 Celsius, right is an electrical circuit with an innovative SMA rapid thermistor. 5. Convection coefficient. After a heating temperature of SMA is measured, the convection coefficient can be estimated. One can use a temperature 113 Celsius and substitute it into this formula. The H is calculated as 214 watts per meter squared by degree K, which is consistent with the number given by literature. Here, the heat conduction and radiation of the metal sheet connected to the SMA wire are shown to be negligible. Now it is your turn, Wang.
Hi, I'm Wang, and I'll talk about the system design, testing, and conclusion. Innovative system design and development. The whole system, including robotic arm and feeding system, as well as gripper system. The first one is the robotic arm and feeding system. The structure and operational principle of the two systems are almost the same. Here, we use linear SMA and bias spring to rotate the robotic arm. About the operation process to rotate the robotic arm. At first, SMA is heated by electrical power. SMA phase changes to austenite, and SMA gets shortened along with pulling a pulling string connected with SMA. The rotational motion is realized through friction force between the pulling string and the friction wheel. Then, cut off the power supply. SMA dissipates heat and is elongated due to spring force. However, during one cycle heating and cooling operation, the rotational motion is limited to finite angles in a forward and reverse way. It cannot rotate 360 degrees. So, we need a mechanism to prevent reverse rotation. An innovative approach is to utilize the ratchet mechanism obtained from corrosion tape and install it to the rotational shaft of the friction wheel. We construct the robot configuration and figure out both required torque and driving torque. According to Flexino's specifications and experimental data of the spring, the maximum driving torque is calculated as 24.2 gram-weight by centimeter. For the maximum required torque, it can be determined and adjusted in realizing the robotic arm or feeding system. About the required stroke, it is determined by the required angular displacement of the manipulator and the diameter of the driving wheel. The length of SMA actuator can be calculated by considering the 4% stroke of SMA wire length in linear actuator. The required length of SMA wire is finally determined to give 14.5 cm. The gripper system. Use V-type SMA to drive the gripper. A normally closed gripper is proposed. In designing a gripper, the key points are opening and gripping force. The force by SMA has to overcome the spring force in order to open gripper jaws. The requirement of gripper opening is 0.8 cm. We determine the required deformation of SMA through gripper configuration and installation of SMA. Then, the length of SMA actuator can be calculated by considering the maximum 14% stroke of SMA wire length in a V-type actuator. Finally, the SMA wire is calculated to give 10 cm for the gripper. About the gripping force, it is determined by the spring force. With gripping force, gripper installation, and the friction coefficient between gripper jaws and object, the holding force of the object can be determined. Overall system. This is what the overall system looks like. We have a manipulator system with a gripper on the top and a feeding system with 3 biscuits on the feeding plate to test the system. In the first open-loop design, the system did not have photo interrupter. However, owing to SMA hysteresis, the stroke produced by each heating cycle is slightly different and cannot provide accurate position control. We change it into a closed-loop control. We glue 3 thin aluminum strips as photo blocking pieces on the friction wheel and use a photo interrupter for the local closed-loop control. Although it turned out more precise in positioning, we still encounter some positioning error. To resolve these problems, mechatronics is employed in the synergetic improvement of both hardware and software. Here, it is noted that the installation of the third aluminum strip is very critical for compensating operational error. This is what our final system looks like. Its circuit diagram is shown. The video shows how the complete system works. the success rate of 10-time tests is 100%. Conclusion. First, a one-year educational project of 76 micrometer SMA wire drive Lego robot has been successfully implemented, and it also demonstrates that non-engineering students can learn and build their own mechatronic knowledge through performing experiments on basic properties of SMA and carrying out hands-on SMA drive robotic projects. Also, for non-engineering students, reuse and craft materials as well as Lego blocks are used effectively to reduce complex manufacturing process. Second, an innovative robotic system consists of rotating manipulator system and feeding system has been implemented, and an innovative rotary actuator which utilizes frictional drive and ratchet is developed. Third, in the development of the pick-and-place robot, functional independence in the robotic configuration and master-slave control is of most importance to ensure successful implementation of SMA drive robot. Last, SMA has high design freedom which makes it most suitable for innovative mechatronic education. That's the end of our presentation. Thanks for listening.